Hi, welcome back to AP Physics C, Unit 6. Still talking about energy and momentum of rotating systems. This is topic 6.6, so this is the last topic in this unit. Here we're going to talk about motion of objects, or more specifically, orbiting satellites. Okay, so in a system consisting only of a massive central object and an orbiting satellite with a mass that is negligible, the motion of the central object itself is negligible. So what does that mean? As I have an object orbiting, okay, we don't care about the rotation of the object itself. Okay, the motion of the satellites is constrained by conservation laws, and we need to look at it in terms of elliptical orbits versus circular orbits. So if the object is in a circular orbit, everything is conserved, right? Mechanical energy, potential energy, and kinetic energy, angular momentum are all conserved. If it's an elliptical orbit, mechanical energy and angular momentum are conserved, but potential and kinetic energies are not. Why? Because in circular orbits, the radius is constant, and in elliptical orbits, the radius is not constant. And then the gravitational potential energy is defined to be zero when a satellite is an infinite distance from the central object. Okay, and this is the reason why we do have an equation that would look something like this, right? U equals negative g central object mass times orbiting object mass divided by r, where this is what is called orbital radius. And that's simply r, the radius of the planet plus the height off the planet, okay? And the reason why it's negative is because we look at the infinite, right? So we just say at a point an infinite distance away, the potential energy is defined to be zero. Therefore, we have this negative sign that shows up in our potential energy equation. All right, so the total energy of a system with a central object and an orbiting object can be written in terms of gravitational potential energy. And so the total energy would be 1/2 of U, or negative Gm, right? Big M over little m divided by 2r. Okay, and so that becomes our total energy. And then ultimately, right, we could talk about escape velocities. There may be a derivation question on the AP test about this, but the escape velocity is just simply a square root of 2Gm over r. Okay, again, m here, I wrote it as, so the m here would be the mass of the planet, the r would be the radius of the planet, right? Because it's going to launch from the radius, from the surface of the planet, and therefore that is why our r is going to be the radius of the planet. Okay, so let's look at an example problem. So we have a rocket of mass m launched from the surface of Earth with an initial speed equal to 1/2 the escape speed. The mass and radius of the Earth are 6.0 times 10 to the 24th kilograms and 6.0 times 10 to the 24th kilograms and 6.4 times 10 to the 6th meters, respectively. What is the maximum altitude achieved by the rocket? And we're going to assume air resistance is going to be negligible. All right, so this problem is more involved than just simply saying, okay, I just could take all this information that's given to me and find R. First thing we will need to do is, okay, what is the kinetic energy as it leaves, right, the launching point? So we're going to have to do some derivations. I forgot the 2. So this is going to be 2Gm over R. We'll call it capital R. Okay, that's going to go here. Right, and so what we're basically trying to do is we're trying to write, in fact, that's not going to go there. Just telling us the escape velocity of the rocket is going to be launched at half of the escape velocity. Okay, so we're going to do half of square root of 2Gm over R, and we're going to square that. okay? And so we have K equals 1/2 m 1/4 of 2gm over r, right? So I square the half, I square the square root. I can do a little bit of canceling here. So this 2 cancels that 2, or one of those 2's. And then I'm going to simplify. So K is going to be 1/4 G big M little m over big R. Okay, so that is going to be essentially our change in kinetic energy, because we're going from 0 to this, or we're going from this to 0, right? Because we're saying what is the maximum altitude, so that at the maximum altitude the velocity is 0. Now we need to figure out the change in potential energy. So it's going to be final minus initial. Okay, so our final potential energy is going to be negative G big M little m over R plus H, right? And ultimately, this is what we're looking for. And then our initial kinetic energy, or potential energy, is going to be negative G big M little m over R, because we're releasing it from the planet. Okay, so plus plus. So we know our change in potential energy, negative G M big M little m over R plus H, plus G big M little m over R. And what do we say? Change in kinetic energy equals the change in potential energy. So 1/4 G M little m over R equals negative G big M little m over R plus H, plus G big M little m over R. So note that they all have that G, right? The G times big M little m. Okay, so this becomes 1/4R equals negative 1/R plus H plus 1/R. All right, subtract 1/R from both sides, and you end up with negative 4/5 R equals negative 1/R plus H. Do the reciprocal. Oh, sorry, it's 4/5R, not 4/5 R. Sorry. So 4/5R. So we're going to do the reciprocal. So 5R over 4, and I'm going to get rid of the negative signs, okay? And then I subtract R from both sides, okay? Sorry, I got these numbers backwards. It should be 5R, 5/4R, which makes this one different. So 5/4R, right? That makes this 4R over 5 that I'm subtracting R from. And so we get H equals 1/5 of R. Okay, if this is a free response question, this is probably what they're going to ask for. If this is a multiple choice question, you may then have to take that number right there, the 6.4 times 10 to the 6, and multiply it by the 1/5 to get an actual number. But as you can see, this wasn't just simply saying, oh, it goes from here to there, and then, right, you note that you have these changes in potential energy, you have change in kinetic energy. But again, when you're looking at it in terms of just an object leaving a planet, energy is conserved. All right, so that's the end of Unit 6. We have one more unit to do, and that's going to be oscillations.